In this example, you're asked to find the inverse of the one-to-one function m of x equals the square root of x minus 4. So first thing, just to find the inverse of a function, I think we'll ignore the graph here for a minute. So to find the inverse of a function, you start by swapping x and y. And so your m of x here represents your output, which typically our output variable is y. So when we swap x and y, we'll write this as x equals the square root of y minus 4. Now you solve for y. Now this part of the problem is pretty straightforward, so we would add 4 to both sides. So we have x plus 4 equals the square root of y. And then to get y by itself, we would now square both sides of this equation. So the square root of y squared will be just y, and this side is x plus 4 squared. We've got y by itself, so that's supposed to be our inverse function. So at first glance, I mean, this isn't a difficult problem compared to some of the other examples you solved. Here's the catch, though. So the graph of this function, it's a quadratic function, so you know the graph's a parabola. The plus 4 tells us that it's shifted from having a vertex at 0, 0 at the origin. It's shifted left 4. So now it's got a vertex at negative 4, 0 here. And then it's just your regular, same shape as the graph of y equals x squared. Sorry, it's kind of on top of our inverse function there. Now, this function's one-to-one. I'm going to graph it in a second, but you'll see it passes horizontal line test. I mean, maybe you know what this graph looks like. I mean, I think you do. Sorry, that seems patronizing. But so the graph of this function, it's that square root graph, so it looks like this, and then minus 4 shifts the graph down 4 units. So the graph of m of x, or you could think like you're plugging in x values. If you plug in x equals 0, you get 0 minus 4. So we get these coordinates at 0, negative 4, this point at 0, negative 4. If you plug in x equals 1, you have 1 minus 4, which is negative 3. That gives me this point here. I only want to plug in nice numbers, so I'm not going to mess with 2 or 3. If I plug in 4, I have the square root of 4, which is 2 minus 4, so that's negative 2. And I'm even going to label these points on the graph. So 0, negative 4, 1, negative 3. This is 4, negative 2. Negative 2. Okay. And it's a square root, so we know it has this general shape, like half of a sideways parabola. So this is your original function m. The graph passes the horizontal line test. It's a one-to-one function. The instructions told us it's one-to-one. Now the inverse function should also be a one-to-one function. So this can't be right. We can't have x plus 4 squared as the inverse function unless we restrict the domain. This is going to need a restricted domain. Otherwise it's not one-to-one. So need to restrict. And that's what makes this problem a little more complex. So what are we supposed to restrict the domain to? We need to be careful. So the way we could determine this is, if you remember, the domain of a function is equal to the range of the inverse function, and vice versa. So the range of this function m, let me make this note down here. The range of the original function m would equal the domain of the inverse function. I wrote f inverse over here. This should be m inverse. Domain of m inverse. Okay, so we can figure out what this restricted domain is for the inverse function by figuring out the range of the original function m. So range, remember, is the set of all y coordinates that are covered by this graph. So the range of m, if we use the graph, would be, okay, so think lowest y to highest y. So lowest y value included in this graph is negative 4. Highest y value, well, this is an increasing function. It doesn't increase very quickly. I mean, I know it starts to look almost flat, but it's not. This function is always increasing. So the range is going to continue to increase without bounds, so we write infinity here. So that means that the domain on this inverse function should be that same. It should be -4 to infinity. So here's your restricted domain. Now the way we usually express that, if it's -4 to infinity, that means that x is greater than -4. I'm going to have to get rid of this graph of the parabola. No, I don't want to do that actually. I'm going to put the condition down here below. So x, our restriction is x must be greater than or equal to -4. There's your restricted domain. So if we keep only the x values that are greater than -4, we're keeping only these points on the graph, so only the right half of the parabola in this case. If the original function was, what would it be? Maybe -x minus 4. So then the graph would have been flipped like this, and then the range would have been -infinity to -4. So we would have kept all x values less than -4 in that case. Okay, so our final answer here for our inverse function, let me get rid of this stuff in the middle, maybe it's a good place to write it. So based on the range of that original function, our inverse function is x plus 4 squared, but it needs to be 1 to 1, so that's with the restriction x is greater than or equal to -4. Which, by the way, so I want to graph this real quick. So it's got a vertex right here. If I want to plot some specific points, if I plug in -3, I'll have 1 squared, which is 1. If I plug in -2, I'll have 2 squared, which is 4. So I obtain a graph with coordinates that includes points -4, 0, -3, 1, and up here -2, 4, which I just want to point out that our xy coordinates have flipped, which is what's supposed to happen with inverse functions. Okay, but so here is your answer to this problem with a little extra information that maybe you didn't ask for.